The Dodge 170, remember that? The Dodge Demon, the last hurrah. It was a very special edition, and it made 1,025 horsepower if you filled it with E85. And they called it the 170 because 85 proof, 170 proof would be 85% alcohol. So we wanted to best that number and best it by as far as we could on regular pump gas. So most powerful V8 in the volume production vehicle. So I added that comment because early when we did the reveal in July of 2020, Flight 25, only last month, we were touting the LT7 as the most powerful American production engine ever. And in reality, it didn't take a lot of research, but it's the most powerful production engine in the world ever by a volume manufacturer. So volume manufacturer, not boutique, not like a Koenigsegg or a special one-off build by Hennessy. It's a regular volume production car, regular volume production engine, highest output engine ever put into a sports car, V8. And not ironically, but by design, the LT7 or LT6 is the most powerful, naturally aspirated V8 ever put into a production car. 8,000 RPM redline compared to the LT6, it's 8,600. No really need to go beyond 8,000. It makes a peak power at 7,000, it just holds it. So you get tremendous acceleration, a lot of power into the power curve, so the vehicle is very fast as a result. Lightweight, low inertia crane train, we want all that revability, and fast revving was really important all the way to redline, because we really love that character for the Gemini engines. All right, a little bit of a history lesson. So we started actually working on these two engines a long time ago. Even before the C7 was introduced, we started thinking about what we're going to do for the mid-engine. Tad was really insistent we wanted to do a mid-engine. You heard earlier this morning the C7 didn't make it as mid-engine. It became a front engine rear drive, but the mid-engine was far behind. And we started thinking about what engines would we build to put in these cars for the Z06 and the ZR1. So I do have to give a little bit of credit here. Mark Royce was very insistent and very helpful in getting these architectures approved. Because he gave us a vision of what he wanted. He was looking for something that had high revvability. We kind of knew that wasn't going to be a push rod engine with all the Valvetrain mass. They're not really great at about 8,000 RPM. We wanted tons of power. Small blocks, we could make tons of power. We had ideas for bigger superchargers. At the time we had the LT5 supercharger that we were working on. We could have gotten a lot more out of that package if we wanted to, but we wouldn't have the character that he was looking for. He wanted that fast, revving character. And a double overhead cam engine design seemed like it was a really good option to get there. So as he was telling us some of the features that he wanted on it, we realized this is going to be a really expensive engine. So he gave us permission. We asked him, okay, Mark, we can do what you want, but this is going to be really expensive. Are the handcuffs off? Are you going to limit us on cost? Are you going to limit us on the technology we want to use? No handcuffs. Do whatever you want to do. Make it the best possible engine you can make for the LT6 and the LT7. So I'm very proud of the fact that they are two of the most expensive engines in the GM lineup. Well, I know my boss is probably not really thrilled to hear me say that, but they are not cheap. But it's just a testament to the fine engineering that can occur when you're unconstrained, and these two engines exemplify that. So we did start work actually in 2010. I looked through my files before I put this presentation together, and we started the initial designs in 2010. And some of the backstory is, remember that old Cadillac CT6? We had an engine that was very short-lived. It was a twin-turbo, 4.2-liter LT8. It had turbos in the valley. It was a beautiful, very refined luxury car. But for whatever reason, it got canceled early, and we only ended up making about 2,000 of those engines. We were trying to use that architecture to be common with these other two engines, and that engine just didn't have the architecture bandwidth, so we got permission to make it a separate, unique design. So that was starting in 2010, and then we started to get very serious on the actual design work in 2014 when the program's approvals were starting to roll through in the affirmative. So these are conceptually the earlier designs. And like Josh mentioned earlier, we're always trying to be very secretive. We try to hide the RPOs. Everybody likes to look for the RPOs that we come up with. So we came up with the nickname Thelma and Louise, based off that old movie with the two women. And they went over the cliff at the end. So the ending wasn't the best part for our program, but the name stuck. So we called them Thelma and Louise. Thelma being the LT6, Louise being the LT7. So you can get a good look here. There are some significant design differences. look at the intercoolers on top of the intake up here. Let's see if I can make this pointer work. Oh, there we go. Right up there. That was an older design, and I'll show you a mock-up of that in a minute. Our first SLT stereolithography model of that LT7 that we made in 2015. And we do this as part of our design process. As we evolve the engine design, we actually make parts, and it's out of a sintered nylon, and it gives us an idea how things fit together, if we're going to have any packaging issues with the turbos, can we assemble them. Every step of the way in our team, we always have our manufacturing engineering team that's working side by side with us. That includes somebody on site with us, who's an integrated part of our team, as well as making sure we're very tight with Bowling Green and the manufacturing engineering staff here. So these were very helpful. And here was the first alpha engine a year later, the actual first running engine. So you can see the intercools are much different today. Packaging-wise, this would have been easier for us, but the problem was that we would have throttle bodies that would be before the intercooler. So the turbochargers, they compress air. When you compress air, they get really hot. So we were blowing hot air through these throttle bodies at about 400 degrees Fahrenheit, and it was just over-temping the throttle bodies. And you don't want to compromise your throttle body durability, because without the throttles, the engine can go unthrottled, and all bad things can happen. So after giving it a good go and trying to come up with alternatives and ways to cool the throttle body, talking to suppliers who can give us higher temp throttle bodies, when we realized there was no hope, we changed the design significantly, and we went with intercooling that would be upstream of the throttle bodies. So here's some historic photos from our engine build area in Pontiac, Michigan, and some of the engineers, Alex, Steve, and then our engine builder who's since retired. And then our first gamma. So you'll notice a trend here. When we build our prototypes, we start with different phases. The first phase is a lot of analysis, and we make SLA models. So the analysis is a very big, important part of our development. And a lot of our analysis models are exceedingly good. A lot of the stuff we do in-house, developing our analysis code for combustion, for volumetric efficiency. And there's an expert in the audience, Jerry Clark, who's since retired a couple of years ago, but he led the team that did a lot of the analysis work. So when we do a new small block, like the LT2, and whatever we do, replace the LT2, which is going to be a Gen 6 engine. And I can say that, even though it's a secret, we made it public about a year and a half ago, that we're doing Gen 6 engines. We start with analysis, and analysis is really good when it's dialed into the configuration of the engine. So our analysis tools have a long-standing history with our push-rod small block engines. This was all new to us. We weren't really sure, how the analysis was going to correlate to the actual running engines. So getting that correlation was extremely important to be able to continue to refine and use the analysis tools. So think of it as the analysis tools being calibrated based on output of real data. So the first gamma engine, so you can see it's got the configuration that we have today. We would start with the analysis. We'd go with alpha, 1 or 2 engines, a complete mule prototype. Then we'd go to a beta, make a few more of those, and those engines are only used in our dynamometer facility, where we do our own internal testing. They don't go into a car yet. And then we go to the gamma phase, which is when things are getting really real. That's when Josh and Taj has the cars ready, the car prototypes. We have to put engines in the cars. So we're building a lot of these gamma engines. We got to make sure that these gamma engines do what they're supposed to do. And that means making the power, making the torque, heat rejection, and then also being somewhat durable so they get their work done. So here is the LT7 exercising itself on the dyno. So I'm going to back up for a minute because I forgot an important thing. This particular engine, was we're doing the analysis, or the calibration of the analysis tools. On dyno, first time, got it broken in, we're getting ready to do a power run. We're going to be very cautious, so we left the wastegates wide open. So a wastegate is a pressure relief valve for the turbocharger. So if you've got higher pressures, you want to reduce the power, you open the wastegates. So we size those wastegates to make sure that when a wastegate is wide open, we can lower the power enough that we can control the torque of the engine where we want to control it. So these turbos, I'm going to explain in a minute, are some of the biggest gasoline engine turbos ever put on a gasoline engine. They are huge. 76 millimeter compressor wheels, a 67 millimeter turbine. It's almost the size of the Duramax turbos that we use. So the wastegates were very large. So we put the engine on dyno, we're running the engine, the wastegate's wide open, we look at the power meter, 850 horsepower. That was our target. So Josh didn't say it earlier, but our target for the program was 850. So we did everything we could to make sure we could meet 850, but since it was all new architecture for us, we put a little bit of extra in there just to make sure we had some headroom if we ran into problems. But when we saw 850 out of these turbos with the wastegate wide open, we knew we were going to make a lot of power. And so then the negotiations had to occur with Josh and Taj, and we work very collaboratively as a team. It's a one-team thing, but it's really important that you don't overpower the car. Because the car is designed with a certain amount of cooling. And if you saw the rolling chassis out there, it's got a lot of heat exchangers. One for the trans, one for the engine oil, one for the intercooler, 3 for the engine coolant, and also it has the AC compressor condenser in the front. So all these heat exchangers, you've got to make them a certain size, they have to reject enough heat. So if we do all the design work for 850 and we come along with 1,000 horsepower, well, the car doesn't work anymore. It doesn't cool, it gets too hot. So it's a fine balance of walking back and forth, a lot of iteration with Taj and Josh and the Corvette vehicle team as we start to develop this engine. But we knew this one was special. After we saw 850 on the power meter, we knew we had something we were going to be able to make a ton of power. So we started to negotiate to ratchet it up. Can we do 900? Can we do 950? And the race was on. So first gamma engine. There it is running. It gets pretty hot. Exhaust gases coming out of the turbocharger, about 1,030 C. And I've got this next one. I hope the audio plays. Anyone get the audio to play? Oh, there we go. All right, that's what 1,064 horsepower sounds like. I was hoping they ramp it up. Can you play it louder? It almost sounds like that. But look at the exhaust. Look how it's glowing red. It's just cool to me. Historic day, power certification, April 15, 2024. So when we were ready to do the power testing, it was a very exciting day for us. We had an internal target. We had a couple of them. One we knew we were going to make 4-digit horsepower. We had a mantra for probably 3 years now. It's got to be 4 digits. So it was really it was something we were all aiming for with Taj, with the vehicle team, with our engine engineers and our test engineers. So we did expect we'd easily be able to get 1,000 horsepower. We wanted 1,026 at the worst, so we have one more than the Dodge Demon. And then the Cal engineers started to work their magic. And one of them is here today. Stephanie, are you here? I think she's sitting in the back. Stephanie was one of the ones who helped develop the LT7 and help us land this power number. She wasn't at the actual test. We had 3 other engineers, a gentleman by the name of Wes Haney, Josh, or Jason. I forgot Jason's last name. He was also at the test site, and then Julie Starr. And we were texting each other and eyeing each other back and forth throughout the entire evening as they were running this power test. So normally we run a power test, it's a couple hours and we got the number. This took 2 days. And the reason why it took 2 days is because the engine was really brutal on all the equipment in the dyno. It was hard on the dynos. The dynos that we bought for this development program, we had none in GM. Of the 86 dyno cells we had in the lab, none of them had the power potential to handle what this engine could put out. So we bought 2 or 3 700 kilowatt, 1,000 horsepower dynos. And even at that, as the engines were running, they would get hot. There's a lot of temperature limits on the dyno. So for this particular power certification test, it involved setting a test point and letting things stabilize for 5 seconds. And then we would take data for 10 seconds. And then we reduce the engine speed and the load down to idle and let the dyno idle for 10 minutes. And over and over and over again. But then as we got to higher engine speeds, the dyno would overheat, so we'd have to back down again. The exhaust stacks would overheat. We had to add water cooling in the exhaust stacks and the dynamometer to keep the exhaust stacks cool. And then later in the evening, when we're the only engine running in the cell, the facilities guys came running over that our emission scrubbers are going crazy. What the heck are you guys doing? And they wanted to shut down our test. And we convinced them that would be a bad idea, so we just kept running. And through Wes and Jason and Julie's work, they were able to land 1,064, and we were just stunned with the number. So I've known this number since April. I'm still stunned. It's just an incredible power number for a gasoline engine only. All the competitors out there, the $1 million Ferraris, the SF90, they have numbers that they don't even come close to 1,064, and that includes the electrification. Most of the Ferraris are really powerful V8s, just the engine alone's about 700 some odd horsepower. So something really special. And then we dropped it on July 25th when we launched the vehicle. And the headlines were just great. So we shared all the headlines amongst the engineering team, and everybody's high-fiving each other. This one we loved, Euro shaming, 1,064 horsepower V8. And the other thing we're really proud of, the number of course we're very proud of, we kept this a secret from some of the most cageous journalists that are out there. And one of them is sitting here in the front row, Ip Halverson. And another one, a friend of mine, and I got to know a lot of these journalists over the years, and they're great. Don Sherman. Did anybody know Don Sherman? Don Sherman. Oh, Don. He is one of the best at finding out secrets. He's got sources everywhere, and he'll always surprise me. Hey, Jordan, what's that LT7 going to put out? Well, how do you even know it was RPO was an LT7? He digs and digs and digs. He's very effective at it. Very polite, very respectful, but man, did he dig. So it was about 3 years ago when our 850 horsepower target was leaked. So somehow some disgruntled employee at a supplier knew the target, and they leaked it to the press, and the whole press went with 850. So we saw that, and we think, oh man, how did that leak out? Oh, this could be a good thing. Let that 850 horsepower number ride. So we never said anything against it. We just kind of let the rumor keep building and building for 3 years, and the press was convinced we're coming out with 850 horsepower engine. So they were totally shocked and surprised when we revealed it 1,064. And the minute we announced that, I texted Don Sherman. Don, I can't believe it, I fooled you. So he responded, Jordan, yeah, I got that one wrong. But I'm waiting for your next version. I know what you're going to be doing with your next version. And he was half right. So we had a lot of fun with that. And it was really a funny thing. Great headlines. America's most powerful. Actually, I wanted that to read the world's most powerful, but this was already went to press. And these are some of the others. Monster, the story behind the Corvette LT7. A shock to the supercar system. Dream V8, and just the good news just kept rolling and rolling. So for us, for my gearhead team, all passionate gearheads, just like you are, they love seeing these headlines. They live for this. They were working 10 years on this engine, and they finally get to reveal it to the world and get all these accolades. I can't tell you how much it warms our hearts when we hear from you, customers, and the press, that they're so appreciative in acknowledging the work that we've done as a team. And I know I speak for Josh and Taj and their whole team, they feel the same way. So Mike, I give a lot of credit to my team there, great group. There are a lot of unsung heroes that develop these cars and these engines that never get the glory. I'm really lucky to be able to be up here and speak to you today. There's a lot of other people in my place on my team who are equally qualified and deserve this just as much credit. And I'm sure Taj and Josh can say the same thing. So you read the history. For me, I'm a big history buff. I read about Zora. I've met Gib. Gib was here yesterday. I met Gib at Taj's retirement party a couple weeks ago. He's a hero of mine. He's one of the unsung heroes that worked side by side with Zora, and he was one of the engineers that actually made stuff happen. So there's a lot of people like that on our teams that make stuff happen, and just don't get the recognition they deserve. A lot of unsung heroes. All right, so a little philosophy there. All right, so program objectives, I kind of went through some of that earlier. Do a quick time check here. LT6, we put a lot of effort in making that the most powerful naturally aspirated. LT7, we wanted the most powerful, period. Both of them were developed together since day one. So Josh mentioned it earlier, we didn't just take an LT6 and put turbos on it. The LT7's purpose-built machine, unique cylinder heads, combustion chamber, turbos, compression ratio, but same architecture as the LT6. So the block is very similar, the block casting, also the Valvetrain with that mechanical finger follower arrangement or finger end pivot arrangement, DLC coated. Exhaust side direct injection, which we think is a very cool technology that was actually developed on our Chevy IndyCar. where we inject the fuel on the exhaust side instead of the intake side to get better mixing, because the fuel is actually spraying right into the airstream as the air is coming into the intake port. So anytime you mix the fuel, you burn more fuel, you make more power, you get better fuel economy, and you also reduce your emissions. LT6 portion of the loop system, and I'll talk about that in a minute. It was also a big thing that was similar. And then turbocharging. So we did choose turbocharging over supercharging. Like I mentioned earlier, we wanted that rev-happy experience. And also, the LT, remember the LT5, 755 horsepower, 100 horsepower to drive that supercharger. So you do have, the engine has to put a little extra to drive the supercharger, where in a turbocharger, even though you do give up some efficiency because of the increase in back pressure, it is more capable of making big power numbers than a supercharger would be. Turbochargers in a front engine car just doesn't work. There's no room for the turbos on a V8 when you put them down low. You can put them in the valley like BMW and Audi does, and you can make decent power, but it's never going to be these really big numbers. So we did choose turbocharging.
How are they different then? You said what they share. How are they different?
I'm going to show you that. Good question. Thanks, Jeff. All right, unique parts, block for the LT7. So the block has additional machining for some of the lubrication. And the oil pump, this was kind of interesting to me, from a gearhead perspective. We showed these blocks to the world with the LT6, and you can see, I can't really see this pointer. We had 7 scavenge ports on the block when we introduced the LT6. And a lot of these journalists, like HIP, for example, I'm surprised you didn't catch that. They never counted the scavenge ports. We were bragging about 6 scavenge ports on the LT6. Well, why does the block have 7? Nobody ever asked, so we hid that little secret in plain sight. The LT7 needed that extra port for the turbos, for the turbo loop. All right, the crank train is also unique. In particular, the cylinder pressures are a lot higher in a turbocharged engine, and the LT7 runs at about 11 megapascals compared to the LT6's 8.5 megapascals. So just a lot more combustion pressure, a lot more pressure on the piston, the connecting rod. So all of those two components had to be strengthened. Cam profile and timing are optimized for a turbocharged engine. Intake with added port fuel system. So we did have to add a fuel system to the DI system that's used only on the LT6. PFI gets a lot of advantages. It does help with some low speed emissions, but in this instance we needed it for the extra fuel. If we went with one fuel injector, the DI, and enlarged it so that it could feed 1,064 horsepower, it would not meter fuel precisely enough at low speed, light load, like idle, and the engine would run rough. So we have 2 fuel systems, and we need to bring on the PFI for the extra fueling. It's always there, but we have really good control of fuel at idle. All right, the air-to-water charger coolers, the intercoolers are obviously unique. The turbos are obviously unique, and then the red line's a little different. This is something I'm extremely proud of, anti-turbo lag reduction, dynamic boost control. The turbo lag reduction, anti-lag dynamic boost control, that's a mouthful. Everybody with a turbocharged engine really worries about turbo lag. And turbo lag gets worse the bigger the turbos are. So that's the lag when you step on the throttle and you gotta wait for these turbochargers to spool up and start to build boost, and then you start to accelerate. If you remember the old horror stories in the 911, the air-cooled 911s long ago, they were notorious for having tremendous turbo lag and making it really tough to drive. We knew this was going to be a problem with these big turbos. We spec'd out enormous turbos, and we were all very concerned that we had a lot of turbo lag. Built the first cars, performance drivers were driving the first cars. The turbo lag was terrible. They reported back, it's hard to drive the car on the track. The responsiveness is so delayed, we kind of get in trouble when we go around turns. It feels terrible. But the anti-lag feature was not implemented yet, and quickly it got put into the software and the calibration, and the development began. And I'm telling you, it's like magic. You drive the LT7, you do not know it's a turbocharged engine. It uses advanced controls where it will actually increase the airflow throughput through the engine when you lift off the throttle. So it'll delay cam timing, it'll change the spark timing, I think it even changes the fuel timing. But the idea is to run the engine a little bit inefficient, so you push more air through it to make the same power, and that keeps the turbines and the turbo spooled up. So as soon as you tip back into throttle, you get the optimum cam timing, spark timing goes right back to where it should be, and you get instant response. and it works incredibly well. So the calibration engineers and software engineers deserve a ton of credit for making this thing extremely responsive. There is no turbo lag. All right, I did talk a little bit about the pushing the dyno to its limits. And I'll show the torque curve again that Josh stole from me this morning. And it is very flat, so it's modulating between about 800 foot-pounds, which are the limitations of the drive line, from 3,500, 3,000, all the way up to almost 7,000 RPM, then starts to drop off. And it would be more peaky if we were allowed to put more torque in there. But more torque, it's really hard on the DCT. The DCT really struggled. And even getting to that 1065, the trans folks were involved every step of the way. Glenn Hofland, who's the ace, had to give us permission to be able to push the numbers to where we're advertising today. Because they work closely with Tramac, the Tramac DCT, making sure that they don't have to revalidate the components. And one of the saving graces for us was that this output was close to what they were already driving for months and doing a lot of validation on for months. So even though we weren't sure of the power number, once we nailed the power number, it was easy to say, well, that's what you've been driving and validating for now, so we should be okay. And so that's why we went forward with that. All right, there's the power. And I think this one is really fascinating to me, because if you walk up through the history of ZR1 engines, it shows on the LT7 torque curve where the power numbers actually are. So the 375 horsepower, well, the LT7 makes that at 2,800 RPM. The LS9, stellar C6 ZR1 engine, 638 horsepower was a huge number back then in 2009. Well, the LT7 makes it at 4,100 RPM. And then our latest and greatest LT5, the LT7 makes that much power at 4,700 RPM, and it just keeps going. So it really is quite a monster. So on one of our last calibration development ride trips, we had a ZR1, 2019 ZR1 on the ride. And the car has always been a handful. It's kind of a monster. It accelerates extremely hard. It really felt sluggish compared to the LT7 ZR1. So probably another worthy mention. When we were doing a lot of the benchmarking, one of the vehicles that we benchmarked was the Ferrari SF90 Stradale. So I don't know how much you know about that vehicle, but it's one of the most expensive Ferraris and one of the most powerful Ferraris. And I think the car cost $800,000. We had a car at Milford for a few years now, did a lot of testing. And I really wanted to drive it when Aaron Link bought it. And he was very nervous to let me drive it. I have a unwarranted reputation of breaking things, so it's not true. Truth be told, the first C7 prototype, very first one, I blew a rod on the engine, the car burned to the ground. Just burned to the ground. Yeah. It was a funny story. All right, since you seem like the human factor part of it, so the cal engineer had the LT1 all dialed in. Jordan got to come out and drive the car. Drive was great. So I'll be there. Vince, it was a Friday afternoon. It was beautiful, a sunny day, fall day. Him and I went out on the track and took it for a lap, did a couple of watts. Wow, Vince, this is great. Vince Collette, you guys remember Vince Collette, Carleton? So I said, Vince, I got to do another couple. Let me do one more lap, and then you're going to go home early. You did such a great job in your team. Let's take the rest of the day off. So we go around one more time. I do another watt, and I hear what sounds like a shotgun blast going off under the hood, and a lot of rattling. And oh, Vince, I think we blew the engine. And I pull out to the side of the road, look under the car. There's oil dripping everywhere, and Vince says, "Yeah, I think we blew the engine." He says, "Let me call security." They have security come and pick up the pieces. So then as Vince and I are standing there waiting, and he looks over at the car and goes, "Jordan, the car's on fire." Wow, Vince, you're right. It is on fire. So we go over and take a look, and then it's engulfed in flames. It's burning. And he looks at me, "Jordan, I don't think we're going home early today." We didn't. So the cleanup crew had to come. The fire department on the grounds came. I think Tom and Carl remember the fire crew. I'm telling you, we made their day. I think they've been so bored, nothing happened in so long. They got to put out a fire. They had the hatchets out. They're hatcheting the car. They're spraying it down. It really was quite fun. All right, back to the current ZR1. The LT7, The Stradale is extremely fast. It's a 760 horsepower, I think, turbocharged V8. It has 3 electric motors. The torque transitions between the motors and the gas engine were just phenomenal. And I think all combined it was 979 horsepower. And when we drove that car 3 years ago, it was stunningly fast because it had effectively all-wheel drive, like the E-Ray. And the acceleration was quite brutal. On this last Cal ride, that car also felt sluggish, like the LT5 and the 2019 Z7 ZR1. So all of us knew at that moment this ZR1 is really unique. It's really special as far as the power and acceleration, especially compared to an $800,000 Ferrari. All right, so for some of the unique features, the block casting I mentioned earlier, we've got a couple little things here. We're feeding oil to the turbos from that little outlet. There's the extra scavenge port. And then we have this passage here, which is part of the scavenging system to suck the oil. Loop system is very complex. The loop system is one of those unique systems of an engine that never gets any credit. But without a very effective functioning loop system, the engine will fail. I like to think of it like the circulatory system in the human body. Your heart, your blood, you don't think about it, but when they don't work right, you're done. And with an engine, it's exactly the same thing. So this particular car, and the Z06 also, the lateral acceleration capability is phenomenal, 1.2 G you can hit on a track. And if you are not able to get the oil to the bearings under those lateral accelerations without air in it, you will fail the engine. So we use a dedicated dry sump system. I'll show you the oil pump in a minute. And it scavenges the bays. So every bay on the engine is isolated from the next bay over. It's a lot like all the race cars do in real race car engine technology, like Formula One and IndyCar. And we actually draw 75 kPa vacuum, so it's a huge vacuum on each of those compartments. So any oil that's floating around inside the engine is sucked out. Just think of it like a Hoover vacuum sucking it out. Puts it in that tank. That tank has centrifuges in it that gets the air out of the oil. So when the pressure pump feeds it back into the bearings, it's solid oil without air in it. These are all the key features that are different compared to the LT6. You can see them here. These here, Josh referenced them earlier, they're Manny turbos, manifold turbocharged, integrated into one casting. And the idea there is to make sure that the exhaust path from the ports coming out of the engine to the turbocharger is as short as possible. That also helps improve responsiveness. So there's the oil pump. It's a thing of beauty. And it's expensive. And then the crank train. A lot like the LT6. And I gotta tell you, these titanium connecting rods, they are like jewels. When I was here 2 years ago talking about the LT6, same thing, they're made by a company named Henkel. They make a lot of Formula One and really high-end race engine hardware, crankshafts and connecting rods. So they make our connecting rods. They're affiliated with a company called CP Carrillo, which makes the pistons. They're out in California. So the pistons and the rods are like jewels. Crankshaft is the same, but since the piston and the connecting rod is hardened, they're a little heavier, so the crankshaft has a little different balance. There, gives you a better look at that. Forged titanium. So you kind of see here on the LT7, the pin diameter is bigger, pin boss is beefier. And all that's to handle the extra pressure. Cylinder heads are unique. LT7, much different geometry than the LT6 and size, all optimized for a turbocharged engine. The other unique factor, everything is CNC machined, so the combustion chamber, the intake ports, the exhaust ports. One of the nice benefits of that is that every engine has the same output. One of the things that, years ago they were talking about, well, I got a healthy engine, mine's not so healthy. There's just a lot of production variation in casting processes. So a cast port may have a little different geometry from one cylinder head to another. The compression ratio may vary a little bit from one engine to another. So some engines put out a little bit more horsepower than other engines. But when everything's fully CNC machined, like it is here, they all are the same. So they all are very consistent in making power. The Valvetrain is common. between the two. Different cam timing events optimized for turbocharging, but it's a really unique system. It's very lightweight, titanium intake valves. We have this finger and pivot arrangement, so it keeps a lot of the mass off the Valvetrain so you can rapidly rev it. Dual springs. And each of these valve clearances are individually lashed by a robot and bowling crane. Other unique things, higher exhaust temperatures from a turbocharged engine, 300 degrees higher. So interesting, the exhaust valves in this engine are a metal alloy called mnemonic. I don't know if you've heard of the mnemonic before. Inconel is usually the standard when it comes to having a high temperature steel capability in exhaust valve. The mnemonic is even beyond a little bit of stuff above that. So I did a little bit of history on mnemonic. I didn't do it on mnemonic, I did a little history on a Corvair, because my son and I bought a Corvair. And oddly enough, mnemonic was an alloy developed by Ed Cole and his team for the Corvair engine, because the air cooled it ran really hot. So that alloy was actually developed for Corvair, and it's still used today on high performance cars. And there's the beautiful intake manifold and cover. Much different in volume. Tuning turbocharged engines versus a naturally aspirated engine. The actual intake volume is much different. We had 23 liters of intake volume on the LT6, and all that's for Helmholtz tuning. But turbocharged engine, responsiveness is king, so we shrunk it down to 9.4 liters. Big reduction. And the other thing we're really proud of, if you haven't seen it yet, is look at that engine cover. It's beautiful. That took a lot of time, and over 50 paint samples were evaluated to choose that color and a unique texture. So these intake covers are actually painted by a company called Pacelli and Vella in Modena, Italy. And you can guess what other manufacturer they paint covers for. It is Ferrari. So Ferrari does a lot of things well, and their crinkle paint on plastic is really something. And it's this company. And then the turbos. So the backstory on these ginormous turbos. We don't make our own turbos at General Motors. We have suppliers that we buy turbos from. There's quite a few suppliers that we use. Most of the suppliers said, when we told them the size that we wanted, said, no, we're out. We don't have anything, any frame size of that size, so we're not gonna work with you on that. Fortunately for us, Borg-Warner, with a little bit of convincing, agreed. They've been a really good partner with us. This is a Borg-Warner turbo. And it's got a lot of tricks in it to try and keep the friction down. It does have ball bearings for the wheel. MAR is a high temperature nickel alloy that the turbine wheel is made out of. So turbochargers, they have a tough life. They get super hot. They have to spin to really high speeds. And if you spin them a little too fast, centrifugal force, they'll come apart. And if you get them too hot, they get soft and they come apart. So it's really a fine balance. And a lot of manufacturers will not integrate a speed sensor. We're actually determining the exact speed of the turbo. This turbo will spin at 137,000 RPM, max speed. And if you exceed that, the centrifugal forces can make it come apart. So in order to be able to use as much of that RPM, that pressure as possible, we adapted a speed sensor so we can go right up to that limit. If we didn't do that, we'd have to put a little cushion in there, and we'd have to reduce the speed of the turbo to peak speed, and we'd actually give it some horsepower. So, as I explained earlier, no expense was spared, and we were able to do some really unique things here. The MAR was expensive, the speed sensor, and also an electronic wastegate. So we push it right to the max, right to the limit, and it does make a tremendous amount of boost. 24 PSI peak under track conditions. It actually runs at about 20 PSI under normal conditions. So what's the difference? The turbo is pushing mass of air. So in order to get the mass of air, somebody has to push on it harder when the air is hotter. Days like today, it's really hot around here. We would increase the pressure, the boost, in order to get the mass we're looking for. This is a hard chart to explain, but I'm going to give you the layman's version. Lower is better. It's more responsive as a function of RPM. So without the dynamic assist and the anti-lag boost control, this is the responsiveness in blue. With all this stuff working the way you want it, look at the response. It's almost instantaneous. Works extremely well. It's really a neat development. Can't wait for you to drive the car and see for yourself. There's the fuel system, the PFI and the DI. Lots of fuel. And at full tilt, 1,064. What's that? I'm sorry, I can't hear you.
Who is the supplier for
We use Bosch for the DI system, and I think we have Bosch injectors for the PFI system, but the rails are made somewhere else, the PFI rail, and we assemble them ourselves. Yeah. So you can get an idea of the fuel flow. On the PFI system, 42 pounds per hour, and 190 pounds per hour on the DI. So DI really kicks it. 5,000 PSI, really great for atomization and combustion. So Josh just mentioned earlier, you're going to steal my thunder, at full power, the engine consumes 2 gallons of fuel a minute. So it will drain the tank. If you could do that in a car in 9 minutes, it'll go through 18 gallons of fuel. So that's another, we're really proud of that. Other crazy fact, and there are some fun facts, some of them are kind of goofy, but the engine, the flow through the engine is so extreme, from the exhaust tips, it produces 37 pounds of thrust, which we've never had an engine that produced thrust before, but you actually have 37 pounds of thrust. And if you were lucky enough to hear a ZR1 go by you at wide open throttle and you're standing as it goes by you, it's a weird sensation. It does have sounds of an engine, but also of a jet, because it's consuming so much air and it's processing and pushing out the exhaust. It's really remarkable. Quite a machine. And like I mentioned earlier, it was really tough on the hardware and the dyno. So if you want to talk more about the dyno stuff, you talk to Stephanie. I know I'm putting them on the spot here. Where is Stephanie at? Stephanie, raise your hand. She told me not to put her on the spot, so that's why I have to. Oh, she'll go all the way in back. All right, so she's standing up right back there. So go see her. Stephanie Poliza Del Toro. All right, so there's some of the fun facts. The dynos, yeah, I already mentioned all of that stuff. All right, so that's pretty much what I had to share with you today, and I'd sure love to answer any questions you may have. So we've got some time here. Thank you. All right, you just have to raise your hand.
You mentioned Ferrari a few times. So Ferrari is infamous for V8 flat plate cranks eating engine mounts from that internal vibration. And then a competitor in Michigan of yours with the 5.2 liter flat plate crank V8 has their legendary problems with internal vibration on the flat plate crank V8. So how have you managed that for both the LT6 and the LT7?
So that's a really good question. I meant to bring that up, but I forgot about that. So flat plane crank engines are notorious for shaking. They're going to shake like crazy. It's essentially a paint shaker, and it's a second order vibration. The engine will go side to side, and we knew we were going to struggle with that. We actually built a 5.5 liter small block pushrod flat plane low value. We were so nervous. We put it in a Camaro, and if things were going to go poorly, it would manifest in that car, and they were okay. So we started to persevere and study a little bit further. We were only do this flat plane crank. We knew that Ford had a lot of problems, and they were legendary for some of the things that they had happened to them, one of which is they claimed that the oil filter would spin off the engine. And we thought, well, that doesn't make any sense. So our first LT6 engine, oil filter spun off the engine. So we blamed the tech. The tech, you didn't tighten it enough. I tightened it. It was definitely tight. So we put a camera on it and did it again. And sure enough, we could see it start to loosen and start to rotate. So we actually went with a canister style oil filter. But Ferrari, they drive well. We did evaluations, we drove them ourselves, and the driver could not feel a lot of the vibration. So that became our benchmark, that we did not want to exceed the vibration levels or exceed them by far above what Ferrari saw, because we figured that's acceptable. And then our vehicle engineers have an opportunity to try and make sure they attenuate any vibration coming in the passenger compartment of the car. So we also knew we wanted more torque than Ferrari. and displacement is torque. So that's why our engine's 5.5 liters. We wanted as much displacement for low end torque because Corvettes and Corvette owners and everybody loves low speed torque because it gives you a lot of responsiveness. So we iterated the bore and the stroke, and titanium connecting rod was a big contributor. So that our lightweight components and our stroke, when we looked at that displacement compared to a Ferrari 4-liter that they were selling in the 458 with a conventional iron connecting rod, were pretty much equal. So we maximized our displacement while trying not to exceed their vibration levels. Even at that, it was a nightmare. I'm telling you, I'm not going to sugarcoat it. The engine sees all that shaking. We had electrical connector fretting problems that just did not seem to end. We would have pipes that would go into resonance that would fail. And it was just not, it was whack-a-mole, trying to fix one problem after another surface. So it is very difficult. Flatline cranks are a headache. They do a lot of remarkable things, but the shaking is really tough. So it took a lot of time to dial all that in. Good question. Okay, next question.
How much does the engine weigh?
Oh man, that's a good one. I used to know. So all small blocks typically weigh 220 kilograms. I think this one came in about 247. It's a little bit heavier. I'm not 100% certain on that though.
You know what oil this engine is going to use yet?
Yep, 550. We're going to go with the Mobile One Dexos R 550.
So it's the same as the LT6?
Same as the LT6, yeah. We actually developed those two oils for the LT6 and the LT7. So the extra viscosity was really important in order to make sure we kept the windage in the crankcase low, and also it helps in a lot of other areas to viscosity when things get hot.
Is that 9.8 quarts for that engine, or what is, how many quarts?
I think, man, I don't know exactly. I think it was 7 that we had in the LT6. It's the same in the LT7.
And what's the mileage?
Fuel economy?
The fuel mileage, yes.
Wow. You guys want to talk about fuel economy? We worked for 10 years on horsepower. Okay, so I'll give you the official answer. The fuel economy testing is not complete yet, so there's no label numbers released. But my experience driving the car, I drove one for a week, about 2 weeks ago now, it wasn't much different than an LT6 when you drive it normally. It's very thirsty though. 1,064 angry ponies require a lot of fuel. So if you drive it like I do, I've got some pretty low fuel economy numbers, but I'm driving like an idiot.
Thank you.
Okay, so I'll fess up. I had one trip. I'm proud of this one too. I got 9 miles per gallon, but it was like it was a shorter trip, and I was doing a lot of demo rides with a lot of items problem. Yes. Next question.
So I haven't seen anything yet, but is it safe to say we're going to be sub 2 seconds 0 to 60 and maybe sub 9.25?
We're probably not going to be sub 9. I've seen the numbers from some of the development trips already. And as far as the 0 to 60, there's not much more we can do due to traction limitation. So ironically, Stingray, 2.6, Z06, 2.5 or 2.4, E-Ray 2.4, they're all grouped pretty closely because we're pretty much at the mercy of the traction limitations of the tires. Where this car comes alive in the quarter. The quarter will be under 10. So Josh mentioned like 9.7. I've seen lower numbers than that, at over 150 miles an hour. So it'll be definitely in the low 9s. If you put slicks on it, you may actually get below 9. Next question.
Yeah, when you harden the gears in the gearbox, what material did you use?
Oh man, that's a good question. Stefan, are you here? Do you know, Stefan? No, sorry. I just don't know. Steve?
Josh won't tell us, but he thinks that it's going to be way over 212 miles per hour. What do you think this engine's going to generate?
I can't tell you. If it's not way over 212, I'd be really disappointed.
Really?
Disappointed. So I think the top speed testing is going to happen this month. There's a trip going out to Papenburg, I believe. So you and him should go out there and photograph it. Yeah. Yep.
Okay, I admit it, I drank the 850 horsepower Kool-Aid.
Okay, I have to applaud that.
And I missed, and I did miss the 7 scavenge port. But if one of us had caught that, what were you going to tell us?
No comment.
Okay, the last is a serious question. The turbocharger speed limiter. Okay, so now what is going on in the engine computer if that speed limiter says, "Oops, you're over speed"? What you open the wastegate or?
Yeah, there'll be a rapid action taken to try and limit the speed. So it'll modulate, it'll monitor it as it gets way up there, it'll modulate, so it shouldn't be in any danger of ever exceeding that.
And what kind of speed sensor can live in that high temperature environment?
That's a really great question. I've seen them, I don't understand the technology, but yeah, it's a wicked environment for a speed sensor.
Can you explain how you use fuel usage between port fuel injection and direct and in what conditions? And also, do you have to do anything with bearings, minimum fill thickness characteristics, because of the differences in the peak firing pressures between the LT6 and
Yeah, good question, Barry. As far as the fueling, I should say in a theoretical sense, we would have only used the PFI when we were going for peak power. But we found that there were some advantages to using PFI at idle because it's less noisy. So we do PFI at idle. And then when we do a driveway, it'll transition into DI. And then there's other conditions where we'll use both. There's some areas on the engine map where it helps for emissions, it lowers engine outs. And also a little bit of efficiency gain. So it's a little bit of variable. But mostly idle PFI, mid-range will be DI, a mixture of the two, and then at peak power it's going to be a mixture of the two. The bearings? Yeah, the bearings are the same as the LT6. So we're really close with our bearing supplier, Tenneco, on the bearings, and they have the material that we're using. They do recommend, and I guess I should probably reiterate this for all engines, they do deserve a break-in. You got to give them a light break-in, be very, very easy on an LT2, LT6, LT7. As the bearing takes a little while for it to actually bed in and add the clearance in the bearing where it needs to be. And the reason is it's pretty simple to understand. The crankshaft is machined, it's round, and the bearing is machined and it's kind of round. But when the crankshaft rotates, it has an oscillatory motion. So it'll oscillate, and it has an orbit. And it takes a while for the bearing, the top coating of the bearing material is malleable and it moves around. So over time, when that orbit occurs, it'll provide a little extra clearance where it needs a little extra clearance. If you really push it too hard before it's moved out of the way, you can get a touch condition where the bearing material hits the journal of the crank